Okay, all right. So have you seen the nanowires, the universe, the big thing? And now I'm gonna take it back again to the nano world. Okay, so here's James Garner, who I had the pleasure to work with him quite a few years ago. We worked on a summer project. So he's a person who can, get really excited when he sees the work in progress, when he does things in a lab. And then later he decided to focus on some other things. So this semester he decided to come back and continue the work. So let's see what he did.
All right, thank you, Dr. Shi. I'm James Garner. I'm not the actor, but you probably got that already. And my work was on the fabrication and characterization of zinc oxide nanorods under Dr. Shi. And so a little bit about zinc oxide. It's a direct band gap semiconductor with a large band gap, so the material is able to sustain large amounts of electric fields. This makes it a really useful device for photoelectric applications. Because we're dealing with nano wires or nano rods, you can fit a lot into any given surface area. So you have a very high density of wires being used to transmit photons. So in a solar cell, for example, you could harness a lot more sunlight per unit area. Another property is that they can be conductive and transparent. So if you were to have a window, for instance, that had a thin film of these wires on the surface, you could conduct electricity while being able to see out the window as well. And their hexagonal crystal structure creates piezoelectric properties, which means they respond to voltage and they can change dimensions, and the change of dimensions also can create a voltage. So this is a final product. This was actually the last sample that I made. So we're not quite transparent yet, but that's okay. But to give you a perspective, that's my hand with the needle, or sorry, the tweezers. And so the sample is only about a square inch in any given size. So this is before the process takes place. This is my substrate. So it's basically a piece of glass that has been treated with a thin film of indium tin oxide, which makes it conductive on the surface. And so I had to hold it at that angle because it's actually transparent, so you couldn't see it before. So that's just it reflecting the light. But it gets housed in the deposition cell in this little area right there. And there's 4 little slots where you can connect indium, tin, or I guess it's just indium, but they're little wires that allow the surface of the glass to come into contact with these holes here and this O-ring, and then that gets exposed to the electrochemical deposition solution where the ions are formed in the chemical reaction. So once we mount the sample, we have to double check that the ITO is face up, because if we have glass interacting with an electrical circuit, glass is a resistor, and so you won't get any circuit completion, no current will flow, and no deposition will take place. So once you can see this little circle right here is the only area of the glass that's exposed to the deposition solution, so that's why it had that definitive shape at the beginning. But then we can take a digital multimeter, take the positive lead and put it onto that piece of glass, and the negative lead can go onto the little pin that's sticking out of the bottom right here, and that's how we can make sure that it's a complete circuit, or at least there's a measurable resistance, so that we know we can go to the next step, which is basically making a solution, preheating the solution, and then preheating the deposition cell also. So 2 chemicals are used in this process. We use hexamethyltetramine, or HMT as we'll call it, in DI water, and let that mix until it's totally homogeneous. So you can add that ingredient first, and once it's dissolved in the water, you can begin adding zinc nitrate, which is where the zinc oxide comes from. But you have to do it kind of slowly when you're adding the zinc nitrate, because if you do it too fast, the HMT and zinc begin to react with one another and precipitates, or little solids, it looks like little pieces of salt basically, but they start to form in the solution, and we want that to take place during the deposition, because those little zinc particles or precipitates that are formed are going to be bombarding the surface of the glass to create this nano surface, or this nanostructure. So basically, I didn't change the concentration between the chemicals. I kept it constant over the course of my experiments. So there were 3 different concentrations of 0.02 moles per liter, 0.01 moles per liter, and 0.005 moles per liter. And so the deposition, once the interior has been heated using this heater and temperature sensor, I used DI water basically to just preheat the inside of the cell. And then once that gets to temperature, once my solution has been mixed and is now completely, ideally is transparent, basically I can empty out what's in the container here and then pour my solution in with a little magnet pill that stirs, and I can connect the circuit using a platinum rod that is inserted into the top of the deposition cell. And the platinum rod is connected to the positive terminal of a 3 voltage power supply. And then the negative side here is connected to an ammeter, which measures the current that flows through the deposition solution as the reaction takes place. And then that ammeter is connected to the negative power supply, or the negative terminal of the power supply, and then those are sent into a computer program that Dr. Shi made that allows us to measure the current over time. And so there are 2 different flavors, if you will, of my processes here. So we have just glass and ITO, and we did several depositions on that surface. And then as a second process, we wanted to see what would happen if we used, if we planted little seeds and let them grow almost like grass. So if you take, we took gold nanoparticles, a solution of gold nanoparticles in water, and we did what's called spin coating. So there's a little platform that has a suction to it, and you put the piece of glass onto it. That table rotates really quickly, and you can drop the gold nanoparticle solution onto the surface, and ideally it would coat it uniformly. So then after taking the gold nanoparticle treated substrate, we take that and heat it so that we can evaporate all the water off of it, so all that's left hopefully is the gold and the ITO. So this is a graph that depicts the absorbance of different kinds of wavelengths of light on just the glass and ITO substrate. So you can see there's quite a peak right here, but that's okay, because that means that it's absorbing ultraviolet light. And we don't really care about ultraviolet light in this application. We're looking at the visible region of light right around here. So yeah, there's a little blip, but more than not, it is transparent in the visible region. So then after we did our spin coating of the gold nanoparticle solution, we used the previous graph as a reference, and this is the difference between the 2 samples. So again, there's a difference in this region, but more or less there is no visible light absorption difference in the 2 samples, which is a very good indicator for us. So we also did an energy dispersive X-ray analysis, and it confirmed the presence of silicon, indium, and oxygen, and which makes sense because silicon is what the glass is made out of, and then indium and oxide for the thin film that's on the surface before we did our depositions. And so you can see that even though I added 5 drops of gold nanoparticles, I don't see any gold on there. So that was kind of a perplexing result when I was going through this, but more or less they were optically identical and elementally identical. So these are graphs that represent the current of the deposition solution over time. And it's interesting because right here you can see that after treating the sample with the gold nanoparticles, we have a higher current reading initially, and then it almost levels to the same, so 1.4 is where this peaks, and it has a little bit less as time goes on. But the only difference between these two graphs, or these two samples, is the addition of the gold nanoparticles. So the concentration of the deposition solution was the same throughout. And so then we changed, and basically I just diluted the solution using some DI water. But again, we have a peak of more current initially, which kind of makes sense because the gold itself is a conductor, so there's less resistance, so that means the positive zinc ions that are formed during the deposition process have, it's almost like they have a direction. It's like, hey, go here, instead of, oh, where do we go? They're all floating around. It'd be like if we're trying to leave this room right now. We have a door that we can all funnel to, so at first it'll be easy for the first people to get through, but then as everybody tries to get through, it'll kind of slow down. So then we have a third sample, which was half of the second sample's concentration, and interestingly enough, we don't have that same initial peak, but this current is much more uniform or constant over time, which indicates that the actual deposition is going to be more constant and uniform because the solution, exactly, it's going to be more uniform, let's just put it that way. So these are images from the scanning electron microscope on the surface at, let's see, I think it's 4,500 times magnification. So the scale bar here reads 10 micrometers, and basically we have a bunch of structures on the surface, clearly, and I took their dimensions. You might not be able to see, but this one reads 4.2 micrometers by 8 or 0.8. So they're longer than they are wide, which as Scott mentioned earlier, that's one of the properties we care about when these nano rods are formed. But they're still micrometers. They're not nanometers, so we're not quite at the scale that we were looking for. But you can see after the addition of gold nanoparticles to the surface is totally changed. I mean, they have similar structures, so this rod is analogous to this one here, but you could imagine that underneath this cluster here is almost little pebbles, and their dimensions are much, much finer. I even have to get close to read it, but it's this one is 0.87 micrometers, 0.74, 1.14. So overall, they're much finer resolution than the original. And here, the only difference, again, was the concentration of the solution. It was reduced from the previous set of images, and left and right, there's one without gold nanoparticles and one with. And I like this image. This one looks really good to me because basically you have a bunch of very defined structures that are going more or less the same direction, and they have the hexagonal shape that gives zinc oxide its appeal. It's kind of hard to see from a distance, but their dimensions are, let's see, 1.4, 1.5-ish, and then we get some of the similar kind of rods or larger structures, but these changed into those. So that one looks really good. And then with the third sample of 0.05 molarity, there didn't seem to be much change, as you can tell. I mean, yeah, there's a little bit less of these larger structures, but maybe that's just the location on the surface that I was looking at. And so my conclusion is that the 0.01 molarity sample after 5 drops of gold nanoparticles gave us the best image or surface, but the current readings from the 0.05 molarity sample was the most uniform. So it might be worthwhile as we look towards the future, maybe finding a region of concentration that's between those two, so maybe like a 0.075 or whatever that half is, and then maybe it would be worthwhile to change the amount of voltage that's being applied during the electrochemical deposition. So instead of 3 volts, have it be 5 volts. Or instead of the deposition lasting for 2 hours, which is how long we ran them, maybe have it for 30 minutes, or change the temperature that the cell is being heated to before the deposition. So there is a lot of room for future research. And here's a reference paper and some sources. And I'd like to specifically thank Dr. Shi and Sonoma State University's Department of Physics and Astronomy, the Koret Foundation for giving us funding for our research, and all my friends and family who helped encourage me along the way.
We have time for 1 or 2 quick questions. Yes?
Yes.
What diameter of nanorods were you trying to make?
We wanted nano rods, so anywhere nanoscopic. We got microscopic.
0.67.
Yeah. So I guess. Let's see. Wow. So on these guys, we did get really small, but they're not as defined. Yeah. So we're looking at hundreds of micrometers, but ideally, we'd like to get to your range, which was like 70, right, nanometers. Yeah.
Cool. Any more? Quick question. You should probably.
You got it.
Quick, so with nano rods versus nano wires, when we're talking about nanoscale, do you still want the length to be longer and it's the width that makes it nano?
Yes. Oh well, the whole scale is nanoscopic, so that's what. Yes. Ideally, they would both be nano. So if we had like 500 nanometer length and 10 or 50 width, that would be ideal. But
Drop that down 1,000 times.
yeah, right. Oh, super easy, right? Tanner.
So you're putting the gold nanoparticles on the surface so you can like kind of use that as like a direction to grow your...
Yes, they're used as a seeding layer.
Okay.
So because, oh, go ahead.
Like the image you had, it showed like kind of like a diamond sticking up. Was that like the top view, like a nanorod like sticking straight up?
Are you talking about this one?
Right here on the right.
Like those?
Is that like growing directly like...
Yes, they're facing upward, and so those are really oriented.
Yeah.
It would be like some of these that are kind of rustled all together, but they're all going that way. So it was interesting. We got the direction, and we got them smaller.
Why are there so many less than like...
It's kind of unique to the sample itself. Like at different locations, you can get different surface topography, and so I think I just got excited on the right image because initially I thought that was what we were looking for, and it turns out it was really close. So on this surface, it's very likely that there are locations that almost like a forest where trees have been cut down, and this is the actual forest. So maybe if I had gone a couple micrometers that way, we would have seen something different. But
Great. Let's